In this video, we are going to start off by looking at the graph of a sequence, and then we are going to move into determining convergence of a sequence. So a sequence, as I had mentioned earlier in another video, is a function. And just like a function, we can graph a sequence. The procedure for graphing a sequence is really very similar to the procedure for graphing a function. It's very convenient to make a table of values. So that's what I have done over here. I've made a table of values. And so in the left-hand column, we put in our values of n, and starting with n equals 1, then 2, 3, 4, and 5, and determining what the output value would be. That would be the value of the term of the sequence. And so when n is equal to 1, we have 2 times 1 plus 3 is 5. When n is equal to 2, we have 2 times 2 plus 3 is 7, then 9, 11, and 13. So just like with a function, these are ordered pairs. So we have the ordered pair 1, 5, 2, 7, 3, 9, 4, 11, 5, and 13. Once again, I want to make sure that you understand that the domain of a sequence is different than the domain of a function, and that makes a big difference in how we actually graph the sequence. With a function, usually the domain is a set of real numbers, with some exceptions for division by 0. With the sequence, the domain is the set of natural numbers, 1, 2, 3, 4, 5. So in other words, the graph of a sequence is not continuous. It is what we call discrete. It is a discrete function, which means it is simply a set of points and is not continuous between those points. So when we plot the points, like here's the point 1, 5, and then there's my next point, I'm just approximating where these points would be. That's the important thing here. And that's supposed to be a straight line, because 2n plus 3 is clearly a straight line. But we do not fill in, we do not draw a line between the points, because it is discrete. Right? And that is the important part about graphing a sequence. A sequent is simply going to be a set of points or a set of ordered pairs with nothing in between. All right, so that is really all there is to the graph of a sequence. The important points is that you can create a table of values. Make sure you understand the domain is the set of natural numbers, that we have a discrete graph, which is just a set of points that is not continuous, so we do not fill in the points in between them. No, we do not do that. Bad. Don't do that. All right, so let me just erase that. There we go. All right, so the next one. Let's take a look at this sequence. So this is the sine function. And so I'm letting n be equal to 1, 2, 3, 4, and 5. And so the sine of 1 is 0.8414, 0.9092, etc., etc. So once again, we can plot these points. Now, the points that I plotted here on the actual graph are a lot more than just these 5 points. But the point that I want to get to here is that this is what we would refer to as an oscillating graph that goes up and down and up and down and up and down and up and down. And we know that is true of the sine function. F of x equals the sine of x. It is also true of the sequence. It is going to be oscillating up and down, up and down. The difference being it is simply a set of discrete points rather than a continuous function. And finally, the third one in my example here, 5n plus 1 over n plus 2. Letting n be equal to 1, we get the output value of 2 for the first term of the sequence. When n is equal to 2, the second term of my sequence is 2.75, 3 and 3.2, 4 and 3.5, 5 and 3.21. And so when we plot these points, we are increasing, but we're getting really, really, really close to this horizontal line right here. And that horizontal line is going to be the line y equals 5. So we'll talk more about that here in a minute. But for now, it's just important to be able to know how to plot these points to graph a sequence. Now, the last thing that I want to talk about is to compare the three of these. The first graph, which was a straight line, as n gets infinitely large, one of the things that we're going to want to do is we want to take a look and say, well, as n gets infinitely large, what is the sequence doing? This is called the end behavior of a graph. And you've looked at that in college algebra. You look at the end behavior of different types of graphs, of functions. Well, we want to know what the end behavior is of our sequence as well. Well, with this particular sequence, as n gets larger and larger and larger, these points just keep going up further and further and further and further. So it's just increasing without bound. As n gets infinitely large, the function value is getting infinitely large. In other words, it's approaching infinity. With the second function, the second sequence, which was the sines, as n gets infinitely large, this function just keeps oscillating up and down, up and down, up and down, up and down between, these high points here and these low points here. And so it just oscillates between, this is what we will call eventually an upper bound, and this would be the lower bound, oscillating between an upper bound and a lower bound. But it is not, it's not going up towards infinity. It's just oscillating between two bounds. And then finally, the third graph, as n gets infinitely large, larger and larger and larger, the sequence is getting infinitely close to the line y equals 5. So what we say is it is converging towards y equals 5. And that's going to be what we're looking at when we get into the limit of a sequence, which is what we are going to be looking at right now. Okay, so the limit of a sequence is, as it says, a fundamental question that arises regarding infinite sequences is the behavior of the terms as n gets larger. Since a sequence is a function defined on the positive integers, it makes sense to discuss the limit as n approaches infinity. So that's what I was just doing from a graphical point of view. And now we want to look at it from a more algebraic or calculus type of point of view. We're actually going to be taking the limit of a sequence to determine what that end behavior is. What is happening as n gets infinitely large? We simply take the limit as n approaches infinity. So let's take a look at this first example. First of all, I've graphed this function. This sequence. If you graph this sequence, and I didn't show the table of values, we know how to do that, but I actually did it in Desmos. So we get these discrete points. And so we can see, just by our looking at the graph, that it would appear that the sequence is approaching 5 as n gets infinitely large. But let's actually take the limit. And so that's what we're doing here, to see if we get the same answer. What we want to do in these next few problems is confirm that what we see graphically and what we do algebraically support each other. So I want to take the limit as n approaches infinity of 5 minus 3 over n squared. Now, using the limit laws, your textbook will talk a little bit about the limit properties or the limit laws. So when you have the limit of a difference, you can take the limit of each term. So I separated it into two limits, the limit as n approaches infinity of 5, and then minus 3 times the limit of 1 over n squared? Well, you may remember that the limit of a constant is the constant. So the limit of 5 is 5. Then, what happens, now a lot of finding limits is very intuitive. We have to think about these intuitively. So as n is getting infinitely large, the denominator of this fraction is getting infinitely large. If the denominator of that fraction is getting infinitely large, then the whole fraction is approaching 0. So the limit as n approaches infinity of 1 over n squared is 0. So we have 3 times 0 is 0. 5 minus 0 is 5. So we say that the sequence converges to 5. And again, that is confirmed by looking at this graph. All right, the next one, we have the sequence 2 to the n over n squared. So if I go to Desmos, or if I plot this by hand, I'm going to get a graph that looks something like this. It first goes down, and then it turns around and goes up and up and up and up. And it appears that as n gets infinitely large, that the sequence is approaching infinity. So let's confirm that by actually finding the limit. And so we're going to have to use L'Hopital's rule. Yes, you remember L'Hopital's rule? And so we are going to use L'Hopital's rule to determine the limit. So the limit as n approaches infinity of 2 to the n divided by n squared. Using L'Hopital's rule, the derivative of 2 to the n is 2 to the n times the log of the base, which is 2. And then, of course, the derivative of n squared is 2n. So if you don't remember the derivative of b to the n, that rule, you may want to go back and look that one up because you're going to use that from time to time. The derivative of b to the n, some base to the nth power. In this case, we had a base of 2. And so the derivative is b to the n times the log of the base. That's the derivative. All right, well, that doesn't really help us too much. Because remember, the purpose of getting L'Hopital's rule is to simplify it to the point where we can actually take the limit as n approaches infinity and have it make some sense. So if we substitute n in here, we get the indeterminate form again of infinity over infinity, or 0 over 0. And so we can use L'Hopital's. Remember, you have to get the indeterminate form to use L'Hopital's rule. So you have to have infinity over infinity, or 0 over 0, or some combination of that. So we're going to use L'Hopital's rule again. And when we use L'Hopital's rule again, we have this in the numerator. So remember that log of 2 is simply a constant. So we have the log of 2 is a constant times 2 to the n. So the derivative of 2 to the n will be 2 to the n times the log of 2 again, but times the constant. The constant has to be multiplied in there too. So we have 2 log 2's. So we have 2 to the n times the log of 2 squared. And so that's where I get this from. And then the derivative of 2 to the n is simply 2. Well, we can now let n be infinity. And so 2 to the infinity is infinity, times a constant is infinity, divided by 2 is infinity. So this limit is infinity. And that is exactly what our graph was telling us. Saying as n gets infinitely large, the limit of the sequence is approaching infinity. So we say that this sequence diverges. The sequence diverges. That's very important. We're going to be talking a lot about converging versus diverging. The limit of the sequence diverges. Let's go to red. All right, the next one. Oh, this is a good one. So if we plot this sequence, it's kind of hard to tell if it's converging or diverging. It's going up, it's increasing, but at a decreasing rate. Now, just because it looks like it's converging doesn't mean that it is converging. Right? Sometimes the graph looks like it's converging to something, but it's really not. It's diverging. And it's very tricky, so that's why we have to actually take the limit to find that out. So in this case, we're also going to be doing some tricky things with finding the limits. So we start here. The limit as n approaches infinity of 1 plus 4 over n to the nth power. What we want to do is just set that equal to y. Set that equal to y. And then we take the log of both sides of the equation. See, once we set it equal to y, we have an equation. And so now we're taking the logarithm of both sides of the equation. Now there's a limit property that says the logarithm of a limit is the same thing as the limit of the logarithm. So we're basically just taking the limit and the log and switching them. Everybody got that? The logarithm of the limit of the sequence is the limit of the logarithm of the sequence. And so now that we have the logarithm on the inside here, okay, we have the logarithm on the inside here, we can use a logarithm property and bring this exponent down in front, and that's what we get here. That's called the power property of logarithms. Well, now we can use L'Hopital's rule. Now, L'Hopital's rule applies to quotients, and we do not have a quotient here. We actually have a product. We have the function n and the function the log of 1 plus 4 over n. But we can create a product, we can create a quotient from a product by dividing by its reciprocal. Just like we can take a quotient and multiply by its reciprocal. If we have a product, we can divide by the reciprocal. We hardly ever do that, but we can do it. And so that's what I did here is I rewrote this from instead of being multiplied by n, I am dividing by 1 over n. So think about that in reverse. It's a more common way of doing it. If you were dividing by 1 over n, you could take the numerator and multiply it by the reciprocal of 1 over n, which would be n. So we're just doing that in reverse. All right. So once we have this, now we can do L'Hopital's rule. Now, the derivative of the logarithm of 1 plus 4 over n, so the derivative of a logarithm is 1 over this, which is what I have here, times the derivative of this, which is what I have here, okay, divided by the derivative of 1 over n. But to save time and space, instead of dividing by the derivative of 1 over n, I multiplied by the reciprocal of the derivative of 1 over n. So the derivative of 1 over n is negative 1 over n squared. That's the derivative of 1 over n. Verify that if you'd like. And so what I did was I just simply multiplied by the reciprocal of that. Save myself some time and space. All right, simplifying all of this, we end up with the limit of this quantity right here. All right, well, now we can actually let n approach infinity. Once again, when we have 4 over n, and n is getting infinitely large, this whole quantity equals 0. So we end up with 4, 1 plus 0 is simply 4 over 1, or 4. So the limit is equal to 4. Now, be careful. Remember, you set this equal to y way back here. So we have, actually it's the log of y, so we have the log of y is equal to 4. The log of y was equal to the limit. The limit is 4, so the log of y is equal to 4. And then using what we know about logarithms, changing this from logarithmic form to exponential form, we have y is equal to e to the 4th power. All right, and so basically because the limit exists and the limit is 4, it converges. So this is converging. It is converging to 4. All right, next up. We have a radical function. And so graphing it, once again, it looks like this is probably converging. Looks most definitely like it's converging, but let's confirm that by finding the limit as n approaches infinity. So this one, we're going to use another little trick. to simplify the radicand. And that is that we look for the highest power. When we have a polynomial function, 1 plus 4n squared is a polynomial function, we divide by the highest power of the polynomial, which is n squared. So we're going to take and multiply by 1 over n squared in the numerator and 1 over n squared in the denominator. Now we can do that because remember, when you divide anything by itself, it's simply equal to 1. So 1 over n squared divided by 1 over squared is simply equal to 1. When we multiply by something by 1, we don't change it. It stays the same. It just looks different. So we're multiplying by 1 in the form of 1 over n squared times 1 over n squared. That gives us this. Verify that this is what you get when you do that. Now, when we take the limit as n approaches infinity, this goes to 0, this goes to 0. We end up with 4 over 1, which is 4. The square root of 4 is 2. So therefore, the limit of 2 is equal to 2. The limit of a constant is the constant. So the sequence is converging to 2. Whatever the limit of the sequence is, that is what it is converging to. And that confirms what we had up here, right? Because it looked like it was converging to 2 up here. And indeed, it is. All right, next one. N squared times e to the negative n. Now this is doing something kind of weird. It starts by going up, and then it goes back down, and it seems like it's getting kind of close to 0. Is it converging to 0, or is it not converging to 0? It appears to be converging to 0. Maybe it's converging to something close to 0. We don't know. This is why we have to find the limit. Is it really converging, and what is it converging to? So the only way to know for sure is to find the limit. Now, to find the limit of this, because if you just let n be infinity, we get infinity squared times e to the negative infinity, and it's kind of vague as to what is actually going on there. So to use L'Hopital's rule again, we can take e to the negative n and change that, put that in the denominator and make it e to the positive n. And so now we apply L'Hopital's rule. This is a pretty simple one for L'Hopital's rule. The derivative of n squared is 2n. The derivative of e to the n is e to the n. And let's do L'Hopital's rule again. And the derivative of 2n is 2. The derivative of e to the n is e to the n. Now I can apply L'Hopital's rule. As n approaches infinity, e to the infinity is getting infinitely large. So that means that this whole thing is approaching 0. When you have a constant in the numerator and the denominator is getting infinitely large, this whole thing is always approaching 0. And so therefore, the sequence is indeed approaching 0, just like our graph had suggested. Next up, n factorial over 2 to the n. Okay. Now, this particular one looks like it is absolutely going towards infinity. It does not look like it's converging at all. And I'm going to have to admit right now that I didn't finish this one because finding the derivative of a factorial is rather complicated. So I decided with this one, we're just going to go with the graphic approach. The other way that you can look at it is from a more intuitive point of view. Some of you may be already looking at some of these limits and doing it from an intuitive point of view. I want you to be able to graph the sequence. I want you to be able to think of some of these limits from an intuitive point of view, and I want you to be able to think of these from being able to do them algebraically. So n factorial. So when n is, remember what a factorial is. 8 factorial is 8 times 7 times 6 times 5 times 4 times 3. 2 to the n, is 2 to the first power, 2 to the second power, 2 to the third power, 2 to the fourth power. Well, here's the truth about a factorial. A factorial gets larger faster than anything else. A factorial, as n approaches infinity, a factorial grows faster than an exponential. So what I'm saying here is that as n gets infinitely large, the numerator, the factorial in the numerator, is getting larger faster than the denominator is getting larger. If you have a fraction and the numerator is getting larger faster than the denominator, it's going to go towards infinity. On the other hand, if the denominator is getting bigger faster, then it's going to approach 0. So if you can intuitively figure out what is growing faster, is the numerator getting bigger faster than the denominator, or is the denominator getting bigger faster than the numerator? And that will tell you whether it's approaching infinity or approaching 0. In this case, from an intuitive point of view, this sequence is approaching infinity, which is what the graph also confirms. All right, last problem. And so in this particular problem, I'll actually use orange. We have a rational function. All right, so graphing this rational function looks something like this. First it's going up, and then it's coming up here, and then it's going down, and who can tell exactly what's going on over here? So we're going to find the limit. And so the limit of a rational function, just like I showed you a couple problems ago, we have a polynomial function in the numerator and a polynomial function in the denominator. When you have polynomial functions, you want to look for the highest power of n. So the highest power of n is n to the fourth. So we're going to multiply by 1 over n to the fourth divided by 1 over n to the fourth. And so that gives us this. 3n to the fourth over n to the fourth minus 7n squared over n to the fourth plus 5 over n to the fourth. 6 over n to the fourth minus 4n to the fourth divided by n to the fourth. Well, canceling out the n's, we end up with this. And again, verify algebraically what is going on here. All right, well, now we can let n approach infinity. Because as n approaches infinity, all right, this denominator is getting infinitely large. This whole quantity is going to 0. This whole quantity is going to 0. This whole quantity is going to 0. All we're left with in the numerator is a 3 and a negative 4 in the denominator. Therefore, the limit is negative 3/4. That means that this sequence is converging to negative 3/4. All right, so this topic is a very, very important topic. Make sure that you understand what is going on, because a lot of what we're going to be doing for the rest of sequences and series is we want to know if something is converging as n gets infinitely large. All righty, that's it.